Section 4.2, Structure of the Nuclear Atom. Here's our objectives. Be able to identify three types of subatomic particles and describe the Rutherford model. All right, we know now that atoms can be divided down into smaller particles, those particles being the protons, neutrons, and electrons. And we even know that those particles can be divided even smaller, but that's beyond the scope of high school chemistry. The electron, in 1897, a guy named J.J. Thomson discovered the electron and found out that electrons are negatively charged particles. And here's what he was doing. He was working with a cathode ray tube. And a cathode ray tube is like what you would find in an older television set, the ones that aren't the flat screen ones. They actually have an electron gun in them. And this is the same thing. You're basically just shooting a beam of electrons from one side to the other. And what he found out was that if you would bring a magnet next to it, it would actually pull the beam of electrons off to one side. Now my roommate and I in college, my roommate thought this would be kind of a neat idea to try, so he had his television and we took a speaker magnet and we held it next to the television, and sure enough it does bend the picture. Now I wouldn't suggest that you try this at home because unfortunately what we found out is afterwards we couldn't get the picture unbent. So it stayed that way kind of for the rest of, forever, I guess. Now, since opposites attract, what we know is if that cathode ray, that beam from that cathode ray tube was being attracted to a positively charged plate, it must be negatively charged particles. Originally, Thomson called those corpuscles, and later that name was changed to electrons. Then along comes a guy named Robert Millikan, and did some more experiments with electrons and found out the charge that an electron had. And, the charge of electron is, we're going to just call it -1 unit. We just kind of arbitrarily set that unit, but that's what it is. And he also calculated the mass and found out that the mass of an electron was 1,840th the mass of a hydrogen atom. So very, very small. In fact, if you talk about it in terms of grams, it's like 9.11 times 10 to the negative 28th, I think, grams. So really, really small. In fact, it is so small that usually we just consider it to be no mass whatsoever. Well, if you take away an electron, and that's negatively charged, there must be some positively charged thing left. And that's what, in 1886, Goldstein discovered. And once again, using a cathode ray tube, found rays traveling in the opposite direction, which he called canal rays. And these positive particles were named protons. So this is the guy who came up with protons. Mass of the proton is 1,840 times the mass of an electron. Then in 1932, an English physicist named James Chadwick found another, the third particle, the neutron. A little bit harder to discover because there's no charge on the neutron, but it does have a mass. So neutrons have no charge, but a mass is the same as that of a proton. And you can see from this chart here some different symbols that they use for the different things. The charges, electron -1, proton +1, no charge for the neutron, and so on. Masses, electron, look, 1 over 1,840th. Basically, once it's, like I said earlier, we're just going to consider that to be 0. Mass of a proton, neutron, both of those 1. And the actual mass in grams, we seldom use that, so we don't really worry about that. We're not going to worry about a mass in grams until we're talking about, a whole bunch of atoms together, a mole of atoms. Okay, let's talk about the nucleus. At this point, scientists kind of thought that there was this uniformity to an atom. They had kind of this idea of a plum pudding. Think of it like some raisins and some pudding, and the raisins being the electrons and pudding being the positive proton stuff, and it was just kind of like that. That's kind of what their idea was. You'd have this positive negative mixture of stuff. Well, along comes a guy named Ernest Rutherford in 1911, decides to do a little testing on this and try to figure out exactly what it was like. And he was using these alpha particles, which is basically a hydrogen atom, take away the electron, you have an alpha particle. So he's shooting these particles through a very thin sheet of gold. And what he found was that most of them passed right through, just like he was expecting to happen, but a small fraction of them bounced off at a really large angle. In other words, in the top picture, you can see all of those just go through. That was the idea. Hey, you're firing like bullets through plum pudding. You know, it's not going to stop. It's going to go through. But what really happened was the bottom picture, where every so often one of them would hit something in the middle and bounce back, or at least really be deflected. And that was very, very unusual. They did not expect that. And here's kind of another picture of the same idea. This is kind of his setup. He's firing this beam through this gold foil, and it gets deflected, and a lot of them get deflected so much that they actually bounce back. So very surprising. In fact, what he said was this was as surprising as if you'd fired like a 15-inch shell through a piece of tissue paper and it had bounced back and hit you. So this is what he decides. The atom must be mostly empty space except for a small area where all of the positive charge and most of the mass is located. And we're going to call that area the nucleus. So the nucleus is that tiny central core. It's where the protons and the neutrons are. And, you know, it's going to look something like our picture, or at least this is the idea. This is the model at the time. You've got the protons, neutrons, you've got the electrons kind of spread around it and, you know, kind of balanced out. Okay. Just to give you an idea of the size of, or how small really, the nucleus is, if the nucleus were the size of a marble, and you took that marble and you put it in the middle of a huge stadium like Yankee Stadium, the electron would fill the entire the electron area, the size of the atom, you know, the rest of the electrons would fill the entire stadium. So the nucleus, just that little itty-bitty marble in the middle, actually probably more like a BB in the middle of that stadium, and the electrons, you know, even though they don't have much mass, they take up all that space as they're zipping around, moving around. So, and the size of an atom is fairly big compared to the size of a proton, but all the mass located inside. And there you have it.